Hi, welcome to our first lesson here in our unit of organic chemistry. So we're just going to go over the introduction, so what is organic chemistry, and we're going to be looking at naming our first set of organic molecules. So first, let's just get into what is organic chemistry, what are organic compounds. So we have terms organic and inorganic compounds are used to distinguish between carbon-based compounds and others. So our organic compounds are going to be carbon-containing compounds, where carbons are bonded to each other, to hydrogen atoms or other specific atoms, mostly oxygen, nitrogen, sulfur, phosphorus, and our halogens. Now, our ionic compounds do not contain carbon, so they will have no carbon-to-carbon or carbon-hydrogen bonds. Now, there are a few exceptions to the rule that have carbon but are not considered organic. So you need to memorize these. So the first ones are the oxides of carbon, so carbon dioxide and carbon monoxide. So these here, even though they do contain carbon and oxygen, which is up here in our exception, technically, when you look at the properties of them and everything like that, they're just not organic whatsoever. Now the other ones are kind of easier to remember because these are all polyatomic ions. For example, carbonates. So carbonate, if you remember, is CO3 2 minus. So you can have anything attached to a carbonate, so sodium, lithium, potassium, doesn't matter. In this case here we have calcium carbonate, so this is not organic, it's inorganic. Same thing here, cyanides, it's a polyatomic ion, Cn minus 1. So those are same thing. The example is sodium cyanide, but we have those. And finally, our carbides. And same thing. Carbide is a polyatomic ion of carbon. So those are not, an ion of carbon, which is not considered organic. And the example I have right here is silicon carbide. So our first thing right here is just kind of looking at how can we classify the difference between organic and inorganic. Now, when we see examples like this is the one listed up above, we have calcium carbonate. So carbonate is one of our examples. So this is going to be inorganic. Whereas our next one, C25H52. Now, I'm not sure the name for this. I should probably Google this and actually put this in. But either way, we can have a carbon-containing compound and just hydrogen. So if it's mostly carbons and hydrogens, it's organic. So what you can do is actually pause the video here now and see if you can fill in the rest of these, which I'm going to do as well, and the answers are going to go up in about 3 seconds. So pause it, see if you can fill them in, and then see if these match yours. All right, and this is hopefully what you've got. Now, a lot of these here are, you can tell we have our oxides of carbon here, we have our cyanide right here, so they're inorganic. Now, a lot of people get this one confused, so CCl4. Now, this one is considered organic, because when you look at our exceptions right here, up here we have oxides of carbon, carbonates, cyanides, and carbides. So we'll notice CCl4 does not fall into this category. It's actually a combination, or if you think of methane as CH4, so all we're doing for CCl4 is replacing the hydrogens with chlorine. And, as we know, chlorine's a halogen, so it fits our description. Alright, so just be careful at ones like that if you do see the halogens. Now, the reason why we have this entire unit is because, well, not only organic chemistry is a huge subset of chemistry, like synthetic organic chemistry is huge, where you look at how to make organic compounds. You can make polymers, which we'll get into later. These are synthetic fibers and all this stuff. So it's a massive subset of chemistry. But what makes it so unique, and so what I think is just awesome, is really carbon, is because, and carbon is very unique. First of all, carbon has 4 bonding electrons, which it can form 4 strong covalent bonds with itself and other elements. And the reason it can form strong covalent bonds as well is that carbon has electronegativity of 2.6, which is kind of right in the middle of our electronegativity charts, which ranges from 0.7 to 4.0. So that means that it will form covalent bonds, it won't form ionic bonds. It's not strong enough to take electrons, nor is it weak enough to lose electrons. So it will kind of form very strong covalent bonds with itself and other molecules. Not only that, it can form single bonds, double bonds, or even triple bonds with itself or other molecules. Now, depending on the combinations, how big, we can get long chains, we can make rings, spheres, tubes, sheets. There's a bunch of different stuff that carbon can do. and no other atom can do this, just carbon. So this is why it's so unique. And we have examples right here of carbon-carbon single bonds, double bonds, and of course triple bonds. Now for these names, we're going to get into how these names actually exist. So just kind of look ahead on how organic chemistry is going to play out. We have organic compounds, so this is our main umbrella thing. Now we are going to break our unit into hydrocarbons and hydrocarbon derivatives. So I'm just going to talk about the hydrocarbon derivatives first. So these are compounds that contain hydrogen, carbon, and another type of atom. So we're going to be looking at atoms that have halogens and oxygen. Now nitrogen, phosphorus, and sulfur show up in here, but we are not going to focus on those families. We're going to focus on the ones that have halogens and oxygen in there. So the four main families of hydrocarbon derivatives we're going to deal with is our organic halides, our alcohols, our carboxylic acids, and our esters. So we'll look at how to name them and how to classify them as well. All right, but that's more later. Now, for our first few lessons, we're just going to focus on our hydrocarbons. Now, hydrocarbons only contain hydrogen and carbon, and that's it. So we have a bunch of different hydrocarbons with different classifications. We have something called aliphatic hydrocarbons and something called aromatic hydrocarbons. Now, aromatic hydrocarbons are structures based on benzene or a benzene-like ring. So, first of all, I know you're looking at this like, what is benzene? Well, benzene is C6H6. And how this looks is going to be like this. So we have what is called a rotating double bond. So you can tell that every second bond within this 6-carbon ring is a double bond. Now, you may see it written like this, or like this. Sorry, getting a little tight on space here, or like this. So there's three main ways to write benzene, but if you see this, like any of these representations inside of a larger molecule, we have what is called an aromatic. Now, besides our aromatics, other type of hydrocarbons that only contain carbon and hydrogen are our aliphatic. So please be very careful and please make sure to review these names. So our aliphatic hydrocarbons, these are going to be straight, branched, or rings of alkanes, alkenes, and alkynes, and cycloalkanes, and cycloalkenes and cycloalkynes, but not aromatics. I know you're looking at this like, oh man, that was a lot of words getting tossed out there, but we have definitions of each one down here. So an aliphatic hydrocarbon, that is an alkane, has carbon-to-carbon single bonds, all carbon-carbon single bonds. Our alkene family is going to have carbon-to-carbon double bonds, whereas our alkyne family is going to have carbon-to-carbon triple bonds. So that's why on the previous page, let this go back. Here we go. On our previous page, we have an alkane. Notice how carbon-carbon single bond, it is an alkane. We have our double bond right here. That was an alkene. Our triple bond, an alkyne. So that's how we can tell the difference with those. So those are our organic families that we're going to be looking at in this unit. Now we're going to start with alkanes today, and later we'll see the alkenes and the alkynes. Now, before we actually get going, as well, for organic chemistry, not only are we going to be focusing on naming and figuring out the compounds, we will need to figure out, well, how to draw them. We're going to be dealing with kind of large organic molecules, and like how I drew benzene and stuff like that for you guys to know. So there's, we have 1, 2, 3, 4, 5 different ways here to draw compounds. The first way is what you would have just learned in Chem 20 and probably just what you see mostly with compounds. That's the empirical molecular formula. So it shows the type and number of atoms present, but it does not tell you anything about the molecular structure whatsoever, which can be challenging for organic chemists, because we need to know the difference between certain molecules, because how the atoms arrange is going to affect the shape, is going to affect their chemistry, and going to affect how they react. So, first, structural formula. This is going to give a clear picture of all the atoms and their bonds. So straight lines is going to represent bonds between the atoms. So if we got C5H12, for example, we can get as long as we draw 5 carbons and all the hydrogens around. So 1, 2, 3, 4. Now, one thing I'm going to do, instead of just drawing everything in a straight line, I want you guys to put a carbon up like this. So, and that's why it says everything can be drawn with straight lines, I know, but we're just representing the bonds now. This is going to make more sense once we get down to the expanded molecular, condensed structural, and line formulas as well, why we want to stick this one off. But either way, we're going to have 1, 2, 3, 4, and 5 carbons. That's fine. Now when we put in our hydrogens, remember carbon can only take 4 bonds. So this carbon right here already has 1 bond to it, so it needs 4. So we go 1, 2, 3. Now it has 4 bonds. This carbon right here, the second one, it has 1, 2, 3 bonds, so it can only take 1. And then the carbon up here needs 3 hydrogens to make 4. We'll notice this one right here I'm highlighting. It already has 2 bonds, one on the left, one on the right, so it needs 1 hydrogen, 2. And then this last one can take 3. Now if you count all the hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So notice how this formula right here, C5H12, yeah, it tells us how much there, but there's no idea on how everything looks, right? And this is how this particular molecule I'm drawing looks. Now, we will notice that this is just straight lines, so the structural formula is kind of the formulas that you would have learned in Chem 20. Now, when we look at the expanded molecular formula, so this shows grouping of atoms, okay? So grouping of atoms would be like CH3, that's a group right here, because carbon, if you remember the word, is a central atom, right? It has a shape around it. So it shows grouping atoms, and brackets are used to indicate locations of substituent groups from left to right. So what a substituent group is a branch. So by writing, I know you haven't heard the word branch before, but as I write the expanded molecular formula, it'll make sense on which one is the branch. Now, how I have this drawn here, you can kind of tell your eye's drawn to the middle here, so we have 4 carbons in the middle. And we can tell this one right here, this 1 carbon is kind of stuck up on there. So we're going to call this one a branch because it's kind of stuck off the middle here. So we're going to use brackets to indicate the location of that, because for the expanded molecular, we only worry about groupings of atoms. So for example, one grouping is going to be this carbon, because it's a central atom, with its 3 hydrogens. So we write CH3. The next grouping is we're going to go over to our second carbon right here. Now you'll notice this carbon only has 1 hydrogen, so we write CH. Now to show this group, or this branch, and once we get to naming the whole thing of an idea of a branch will make more sense, but because this one's kind of stuck off, kind of what we have here is like our main thing right here in the middle, we're going to go bracket and go CH3. So this right here is a branch or a substituent group, and that's how we represent it in our expanded molecular. Our next group, we have this carbon right here, it has 2 hydrogens. Then finally, our last carbon on the end is CH3. So we'll notice that there's no branches whatsoever, there's no showing of the bonds like in the structural formula, right? It's just there. Now, this right here, the expanded molecular, is tough because where you don't see the bonds, it's very easy to hide a double bond or a triple bond, or even here like this branch that's sticking up, right? It's easy to hide it, so I would recommend starting with structural formula first and then getting used to condensed structural. Because condensed structural is basically taking structural and the expanded molecular and creating some sort of a hybrid. Because in the expanded molecular, what we did is we created groupings of atoms around carbon. So condensed structure, we're going to do the same. But we're still going to show all the other bonds are shown except carbon and hydrogen bonds. So, for example, our first carbon from our structural formula is this one right here. We can see C with 3 H's around it. So we go CH3. Then we show a bond between the second carbon. Now this one has 1 H, so we go CH. Now this carbon sticking up from it, we can show sticking up with CH3. Then this carbon here, the third one through our middle, has 2 hydrogens, so we go CH2. And then the last one has 3 hydrogens around it, so CH3. And we write it like that. So this is just a way where we see all the bonds. So if there was a double bond, a triple bond, or anything like that, we'll be able to see it. We just don't show the hydrogen bonds because there's just so many hydrogens there, so we don't want to write it out every single time. Now the line formula is the one that all chemists use, and this one that I would recommend trying to get used to using as soon as possible because it makes life so much easier when you're drawing stuff out. So how the line formula works is it uses lines to represent chemical bonds. All right? Each end of a line represents a carbon atom, and it's assumed to have the maximum number of hydrogens bonded. So, for example, if I draw a line like this, what is assumed that there's a carbon here and a carbon here, but we do not show those carbons. All right? We assume they're here, but there's two there. Now that was two carbons. So that's this carbon right here and this carbon right here I just drew. Now if I want to draw the one sticking up like that, I can go up. If I want to draw the second carbon, it's going to go like this, and the other one goes like this. So what I have here, or what I've drawn, is I have my first carbon, my second carbon, third carbon, fourth carbon. So if I label them, 1, 2, 3, 4, I'll call this one 5, and that line up here is 5. So that's how we use our line formula. Now, once again, you're probably looking at this and you're just thinking, holy crap, this is a lot. And it is. But as we get going, as we start learning how to draw it, how to name it, like all this stuff will just start making more and more sense as we get going. The main thing is just remember carbon needs 4 bonds. That will always be the case. Now, structural isomers. Now, this is a term, be very familiar with as well. So these are compounds that have the same empirical formulas but different structural formulas. So we're going to look at C5H12 again because we just drew it up here, C5H12, right? Now, for one of the structural isomers is the one that we just had, right? 1, 2, actually I'm going to do condensed structural, just because I like that one. So we had CH3, CH, CH2, CH3, and we had CH3 up here. Now this one right here, now don't worry about the names, you guys will learn how to name these as well. I'm just showing you how you can move stuff around and get a different name. So if we had to name this one would be called methyl butane. Alright, so it has a particular name and a particular shape. Now for a 5-carbon atom as well, I can draw something different, and that is what if I stuck all the carbons end to end to end, so I don't have a thing sticking up, it's just one straight line, right? So I would have CH3, CH2, 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 and CH3. 1, 2, 3, 4, 5 carbons in a row. If I drew this one, this is an isomer because if you count the carbons, I have 1, 2, 3, 4, 5. The hydrogens, 3 and 2 is 5 and 2 is 7, 2 is 9, and another 3 is 12. I'm still C5H12. Just like here, I'm still C5H12. But we can tell it has a different structure. And if it's a different structure, it'll have a different name. Which it will. Once again, don't worry about the name. We'll get to that now in a bit. And another one that we can potentially get as well Alright, so if we drew something like this, notice, count my carbons. I got 1, 2, 3, 4, 5. Hydrogens, 3, 6, 9, 12. So I still have the same empirical formula C5H12, but completely different structure and of course different name. Now by the end of this lesson you're going to look back and you'll be able to see how I got these names. But just for right now, I'm just showing you that you can have the same empirical formula, just with, obviously, different structures and different names. Alright, now the reason that these isomers are going to be important is that when we start getting into specifically organic compounds and their properties, so how we draw them is very important. So for example, like 2 isomers of C3H8O, one is going to have a boiling point of 7.4 and the other one is 82.5. And the reason for that is that if you drew out isomers right? So, and this is actually a question out of Chem 20 as well, when we look at why sometimes formulas give you very important things, right? So if we draw it so we have a hydrogen attached to this oxygen, well, this is hydrogen bonding. And remember, hydrogen bonding is a very strong intermolecular force, which will raise the boiling point. So if we drew something that had hydrogen bonding, this is why the boiling point of this particular molecule would be 82.5 degrees Celsius. Whereas the other one, if we manage to draw it without any hydrogen bonding, which we can do by sticking the oxygen actually in the middle, we'll notice no hydrogen bonding, but it does have a dipole-dipole force. I'm just going to short hydrogen bonding HB, so boiling point is equal to 7.4 degrees Celsius. All right, so that's also why isomers are going to be very important, and how we draw them matters a lot. So with our hydrocarbons, where they're just, hydrogen and carbon, it doesn't really matter that much. But when we start getting into bigger molecules and we start introducing oxygen, you do have to be careful about how you draw them, all right? Now, just a little refresher on intermolecular force. I'm not going to spend too much time on this because we would have had a lot of review on this in our Chem 20 review back at the beginning of the semester. Now, for organic molecules, I'm just going to give you guys kind of a quick and easy method to figure out if you're going to have a polar molecule or a nonpolar molecule, and therefore figure out if it will dissolve or not. And this is all right here. So if we have just carbon and hydrogen, it's always nonpolar. That will always be the case no matter what. So when we look at our aliphatics and aromatics, nonpolar. If we have carbon and hydrogen and another type of atom attached, it will be polar. Now, we are going to learn another little asterisk on that, like it depends on the size of the molecule as well, but just for right now, if you see just carbon and hydrogen, nonpolar. Carbon and hydrogen plus another atom, it's going to make it polar. And now, once again, I'm not going to go over all this because I want you guys to kind of look at the notes and figure these out as well. But you can make kind of snap decisions on polarity. Now, once again, drawing structural diagrams you can, but notice just carbon and hydrogen, non-polar. Carbon, hydrogen, another atom, polar. Carbon, hydrogen, non-polar. And take a guess, see a different atom, polar, right? So this page right here, I'll let you guys kind of go through, look at the notes, and get these online. I just want to jump right into the naming, just because this video is already running long as it is. So, naming hydrocarbons. We are going to follow the IUPAC naming system. So that's the International Union of Pure and Applied Chemistry. So these are the guys who made up the rules for naming these here. So there's going to be three basic parts to a naming. We're going to name our branches, and our branches may have prefixes, which our prefixes are down here. So depending on the number of branches, if we have 2, we're going to use the prefix di, 3, tri, 4, tetra, and so on. The other part of the name is going to be root or the parent chain. Now, when we scroll down and see what the root or the parent chain is, the root is the longest continuous chain of carbon atoms present. Now, depending on how long our thing is, if our longest chain is 1 carbon, we're going to see the word meth. If it's 2 carbons, eth. If it's 3 carbons, prop. If it's 4 carbons, bute. Now, you guys already seen this before. Now, if we go back to this right here, notice how the longest chain in the middle for our first one, we had 1, 2, 3, 4 in the middle, bute. And that's 4. We had 1, 2, 3, 4, 5, pent. And here, our longest chain in the middle was 3, so we seen prop. So that's where these names came from. Now, and as for branches, as I kind of brought up that before, if we have our longest chain in the middle right here, obviously this is a branch. And this right here are also branches. Sorry, that's a terrible way to spell branches there. But yeah, so that's where those words were kind of coming into play there. And then finally, the last part of the name is going to be the suffix or the family name. Now, When we scroll down, the suffix indicate the family or the functional group. We'll get into that word very soon, and everything is unique for every family. So all the names kind of have these breakdowns. And to get used to it, you just gotta kind of do a lot to get used to it. So our first family we're going to look at is alkane. It contains only carbon-carbon single bonds. So the suffix, the family name, we're going to see A-N-E at the end. Now our general formula for alkanes is CnH2n plus 2, where n is equal to the number of carbons. So as long as you have a name, like pentane, we know pent is equal to 5 carbons. So if we want to figure out the chemical formula for pentane, we go CnH2n plus 2, C5H, 2 times 5 plus 2, and we end up C5H12. So that's kind of the easy way to figure out what the chemical formula is. So you don't need to look them up every single time, as long as you know the prefixes, the root names, so meth, eth, pro, bute, pent, hex, hept, oct, non, and dec, you can figure out the chemical formula. So let's look at the naming. First, we need to identify the longest continuous chain of carbon atoms. So that means it's one after the other. It's not the total number of carbons. It needs to be one after the other attached. It might not appear in a straight line. There might be groups attached to certain things, but we're going to break into that when we get to our first example. Step number 2. We're going to number the carbon atoms beginning with the N nearest to the first branch or the substituent group. So, before we get to 3, 4, and 5, let's look at our first example here. So I'm going to do step 1 and 2 in the one shot. So step 1 is find our longest continuous carbon chain. So you start at an N. So starting at an N is either starting at this carbon, starting at this carbon, or starting at that carbon. Either one, you need to start at the N. You cannot start in the middle. So if we start, let's say, at this carbon right here, and we count, we go 1, 2, 3, 4, 5, 6, 7, 8. Right now, obviously, if we go in reverse, it's still going to be 8. Now, if I start here at this carbon, I go 1, 2, 3, 4, 5, 6, 7, 8. So no matter what, you can tell I'm going to have 8 carbons as my longest continuous chain. And it didn't matter whether I started here or here. So, just for fun, why don't I go starting here, and I'm going to block off this. So I know my parent is equal to oct, because oct is 8. Now in step 2, it said number the carbons so that carbon 1 is closest to the first branch. So obviously, this right here, where it's not contained inside my longest continuous chain, this is what we call a branch. God, why can't I spell branch today? So this is a branch. Boom. So when we look at our carbons, if we start on this side right here, obviously 1, 2, 3, 4, 5, 6, 7, the branch is on carbon 7. Not what we want, because if we start here and go 1, sorry, just let me get a different color here. If we go 1, 2, 3, 4, 5, 6, 7, 8, our first branch is on carbon 2, which is the lowest number. So this is how it needs to be labeled. Now let's look at step 3. Identify and give the location, so the number of carbon that's on the parent chain, and replace the branch with, basically if you name it like an alkane where you have A and E, you add YL. So if it's a 1 carbon branch, the meth, it becomes methyl. Sorry about that, as you heard, just had a phone call come in there. So if we have a 1 carbon branch, it becomes methyl. Now this one right here that I have highlighted in blue, this is just 1 carbon sticking off. So we are going to call this one methyl, but it's on carbon 2. So it's going to be 2 methyl branch. So that's step 3 done. Now step 4. When a molecule has 2 or more branches, not the case for this one right here, so I can ignore 4 for now. And I'll come back to that when I do the second example for you guys. When we look at number 5, write the complete IUPAC name following this format. So we always label the branch first, but we need to have the number and location of the branch followed by a dash, which I did that right here. So for the name, I'm going to start with 2 dash, that's the number of location of the branch, and the branch name, I named it methyl because it was 1 carbon. Next, notice how there's no spaces right here. I'm going to name the parent chain, which I already have right here. My parent is oct. And then finally, the suffix. What family am I in? And these are the alkanes, and all alkanes end in A-N-E. And the suffix, once again, was written right here, A-N-E. So by following all those, I'm left with 2-methyl octane for this compound. All right, let's look at the second one, because the second one we are going to use our number 4. So first step is we need to find the longest continuous carbon chain, just like before. So there's many different areas we can start with, all right? So I always like to kind of start the one on the left and then just kind of going around, all right? So first chance, like cut right through the middle and see how many you get. All right, so 1, 2, 3, 4, 5, 6, 7. So if we go straight across the middle, we're getting 7 carbons. Cool. Now, I can kind of tell if I start down here, it's 1 carbon, 1 carbon. It doesn't really matter, but I'm going to see what happens. Let's say I go down here and figure out what happens there. So if I go 1, 2, 3, 4, 5, go down, 6, 7, 8. I just created a longer carbon chain by going down. So that means that this is, in fact, my longest continuous carbon chain. And you'll notice I'm only trying to highlight the carbons. So step 1 done. Step 2, number the carbons, starting with the end closest to the first branch. So my ends are here or here. Once again, it's not in the middle. Now if I start down here, 1, 2, 3, 4. My first branch off carbon 4. If I start here, 1, 2. First branch off 2. So I need to go 1, 2, 3, 4, 5, 6, 7, and 8. Those are the numbers. And I'm also going to go, just for my own memory, my parent is equal to oct, because I have 8 carbons. Now, actually, there is a mistake for this one right here. So for those of you that are paying attention, just see what I'm going to do here. So this one up on the top, I want you guys to take your own pencil, erase CH3 right here, and put in CH2. All right, so please make sure to make this adjustment because it's the only way this will work. I just completely forgot to change this one in the notes when I was going over it. So sorry about that. But just make sure your compound looks like this. So let's go back to identifying and giving locations of the names of the branches. So just like before, anything that's not inside my green, any carbons that's not inside my green main chain right now is a branch. So we can tell this one right here is a branch. And we have off carbon 2, and it's 1 carbon, so it is a 2-methyl. Now, notice on carbon 4, we see 1, 2 carbons. Now, when we have 2 carbons is eth. So I write eth, show it's a branch, it's YL. And same thing here, notice I have 1, 2 carbons that aren't accounted for, off carbon 5, so this is going to be 5. 5-ethyl. Those are my branches. Now, step 4. This is going to be the tricky part. So step 4 says, when a molecule has 2 or more branches, list them alphabetically. So, and the reason we list them alphabetically, do not take the prefix into account for alphabetical order. Do not do that. That's why I never wrote di or tri or anything here. I see methyl, I see ethyl. E comes before M in the alphabet, so I'm going to list my ethyls first. So when I start numbering them, I see ethyls on 4 and 5. So I'm going to have to go 4. That's not 4, that's 2. So 4, comma, 5 because there's 2 numbers. Now I have 2 ethyls there. Remember prefixes. So we get diethyl. And that's back on the previous page, right? about the whole prefix thing with branches. So we got 1,2-diethyl. Next, we have our methyl. Now, before, notice how that dash shows up between number and name. So whenever we're separating letters and numbers, we go dash, 2, methyl, and then finally our parent chain oct, and suffix ane. So the name here is 4,5-diethyl 2-methyl octane. I know, that is a lot to take in at this moment. That's why if you actually start right now and go to your in your workbooks that you have listed there, the first thing is just a little bit on isomers and a little bit on alkanes. It's more simplistic alkanes than what we're given here in the notes. So that's a good starting point. Now, if you still want to continue on the next page, we have more diagrams here. All right. Now, I'm going to go back and kind of fill, or actually what would be an excellent time right now is pause the video and try these here on your own. All right. Now, what's going to happen is that in a few seconds, you're going to see everything pop up, but they're going to be popped up the exactly same way how I organized them last time. I'm going to have the longest continuous carbon chain highlighted in green. I'm going to have all the branches highlighted in blue, and I'm going to have carbon 1, 2, 3, 4, all the carbon numbers in red and the name in red. Okay? So please pause the video because in 3 seconds, the answers are coming up. All right, and I know this looks like a lot here, but these are the answers. So our first one right here, we can tell we have 2 and 3 methyl, so we go 2,3-dimethyl hexane for that one there. For our other one, our longest continuous chain is hept. We see branches off, methyl branches off 1 and 4, and an ethyl off 4 as well. So we have to go 4-ethyl, E comes before M, and then 2,4-dimethyl heptane on our one down here. Now, if you took it and went straight across the middle, that's also fine. I just wanted to show you that you don't go across the middle every single time, so I kind of went zigzag up like that. But you still should have gotten 3-ethyl 2-methyl pentane. And finally, the last one, it goes right across the middle for heptane. We see methyls off carbon 2, 2 on carbon 2, and 1 on carbon 3. So we write 2,2,3 trimethyl because there's 3 of them, and heptane at the end. So that is the naming of our alkanes. Now down below, we'll see some stuff on how to draw them. Now, once again, drawing that, you have your directions right there. It's basically you draw your parent chain first and then draw the branches. Now, before this video closes, I just want to bring up one thing to you, and this is this term, saturated hydrocarbons. This happens when we only have carbon to carbon single bonds. If we have a double bond, specifically carbon to carbon, it is going to become unsaturated, which you will see in the next lesson. So just right now, we are dealing with only saturated hydrocarbons. Now, for these here, these examples, once again, you can try these on your own. You can check the notes to see if you get them. And one to really test your ability on drawing and naming. Look at practice 7 here. Draw and name all isomers of C7H16. There are going to be 9 in total. Now, your best bet is to just try it. Draw what you want and try to go back and name and pick apart your own naming scheme. And keep going. And then, of course, look at the answer key later because I have all these done. And just go back and see how many you got. To get all 9 on your first shot, it's challenging for sure, but it is possible doing it. Your best bet is to just draw, try to name it, and then see if yours matches up with what I have. All right? And of course, just make sure that with any of these here, if you just need a little more help, make sure to email or do anything like that. Rewatch this video, or what you can do is just work on your workbooks. Like I said, those are a little easier than some of these here. They're only dealing with like 1 or 2 branches at a time. All right? So that is it for naming of the alkanes and the introduction to organic. Next lesson, we'll be looking at something called cyclic alkanes. There's something completely different, but either way, that'll be on the next one. So see you guys later, and good luck with all of these organic stuff. So please spend time on this because this is kind of the base of organic chemistry right here, is being able to name these alkanes with simple branches. All right, see you guys later.